I'd like to do now is introduce Don Selly, our program director and immediate past president, to introduce tonight's speaker. Don?
Thanks, Joe. I just wanted to make a quick plug for the October 2nd meeting. Walt Cooney is going to do the presentation. Many of you may know Walt. He's a very accomplished amateur astronomer, and he's going to tell us how he observes cataclysmic variable stars and things like that that go bang. So it should be real interesting. And hope you will be willing to be able to attend on October 7th. Tonight, I'm really pleased to be able to introduce Dr. Justin Filiberto. Going back to January, I happened to see a write-up about recent volcanism on Venus, and read the article and got Dr. Filiberto's paper, and the paper was fascinating. So I reached out and asked Dr. Filiberto if he would be willing to give us a presentation on his work on volcanism on Venus. Dr. Filiberto is a senior staff scientist at the Lunar and Planetary Institute, and he's a planetary petrologist and geochemist. His work crosses disciplines and planetary bodies, and by combining his investigations of basalt formation using petrology, mineralogy, geochemistry, and geophysics in order to constrain crustal and mantle evolution in the inner solar system. So he's a real expert on volcanoes and volcanism, which is a real interesting subject to me. I would hope you would all welcome Dr. Filiberto, and I guess we'll have time for some questions after his presentation. Dr. Filiberto, over to you, please.
Thank you, and thank you for the invitation. I am a geologist by background, and I focus on geochemistry. So if I use a term, if I use a phrase or something that you don't understand, please don't wait till the end of my presentation to ask a question. Feel free to unmute and stop me so that you're not lost for the next sort of 40 minutes or so. I'm happy to take questions as I go, since I know this may be outside your normal type of talks. So, all right. Did that work?
Well, we do see it. Yeah, there it goes.
Okay. So my talk today is Volcanism on Venus, evidence for very young volcanism. And I like this cartoon partly. This is actually from space.com article about my paper that came out in January. The original image credit is from ESA. And this is the problem when you do science, is the journalists get a hold of it and make these really lovely cartoons that have little in reality. So we'll come back to this cartoon and show you what actual volcanism on Venus probably looks like. So start with, where are we in terms of how much information we have for Venus? And I love to show this. I also study Mars, I study the moon a little bit, I study the Earth quite a bit. If I put up a list of successful missions to Mars or the moon, you would not be able to read the text. We've had so many successful missions to Mars. We've had so many successful missions to the moon. Venus is sort of our forgotten planet. That these are all of the successful missions, either flybys, which are in gray, landers, which are in red. So the Soviets back in the 60s and again in the 80s actually landed on the surface, and I'll talk about some of those data. And then Galileo flew by on its way to another mission, or other planets, but it did take some data in the 90s. NASA's two big orbiters were Pioneer Venus and Magellan. I'll talk about some of the Magellan results. And then NASA has not sent anything there since then. So it's been decades since we've sent anything to Venus. I will touch at the end, and especially on the recent volcanism, on data from Venus Express, which is a European Space Agency mission. Atsukagi is a interesting mission from our Japanese colleagues, but it's focused on the atmosphere, and so I'm not really going to touch on it. But again, we've had a handful of landers and 4 orbiters plus the Venera orbiters. So we do not have nearly as much information about the surface of Venus as we do Mars, the Moon, the Earth, or any other planet. So I'm going to start with Venera and Vega, sort of here in the 60s. And this is the data that got me interested in Venus. Not that I was working on science back in the 60s, but when I decided to start leaving working on Mars, or adding to working on Mars and working on Venus as well. And if anyone's followed Mars missions, they last for years, if not decades. Well, the surface of Venus is 470 degrees. The atmosphere is CO2 with some sulfur, which means it's caustic. It's hot. The surface pressure is 92 bars, so it's high pressure. And so missions to the surface of Venus don't last years or decades. They last for about an hour at the longest. And so it's a very different style of mission. It gives us great information, but in one specific location instead of driving around and finding out all of that area. So this is the Venera Vega program. It was Soviet launched. There is lots of orbiters. They actually had these giant machines that came through the atmosphere with parachutes here. They landed on the surface, and then they analyzed some of the rocks. And they took the first color photo of Venus as well. And we're going to come back to this when we get to some of my newer results. But you can see here, this is the actual image, and this is after they tried to remove the atmospheric effects and the other effects. And so this is what, in theory, your eye should see. This is the white plate, so for white balance. And you can see these look like sort of rusty rocks. They're sort of dark black rocks with some red coatings. And if you have ever been to Hawaii, and not the fresh basalt, but if you go to where the basalt's been weathered, this is sort of what it would look like: black rocks with, or dark rocks with some red coatings. And so they did analyze them. All of the landers had different instruments, so we don't have the exact same data from all of them. But I'll talk about some of that data in context before we move on to some of the more recent stuff. So this is the Venera and Vega data. This is, I lost my mouse. There we go. Can you all see my mouse? Yes, okay.
Yes.
So this is uranium and thorium, potassium and thorium. And the important thing to look at here is, first of all, the huge error bars. If you looked at data from the Earth, if you look at any of our data from Mars, the error bars are typically about the size of those data points, let alone how much larger all of these are. But the one to point out is the potassium to thorium. Here's the Earth here. And you can see that within error, although not Vernier 9, which is weird, but the rest of them within error look like the Earth. And so I'm going to switch to another way we classify rocks, which is calcium to aluminum versus titanium to aluminum. These are the rocks from Venus. Again, these large error bars. The circle here is terrestrial basalt, so rocks from volcanoes on the Earth. Also in here are Mars soils, and you can see how much smaller those error bars are. But what you can see is these look very much like a basalt, and they look very much like things we would find on the Earth. And so this led to my 2014 paper, where I used these, there we go. I used these analysis and compared them with what we know of volcanoes on the Earth to see if we could tell something about what types of volcanoes and what type of volcanic rock should we, or what do we know about Venus before moving on to the more recent stuff of how old are these. And so we assume an Earth-like basalt chemistry, and we assume that it has Earth-like magmatic processes. And when I published in 2014, both of those were assumptions. They're pretty well constrained now. And then I also work in a lab, so I'm going to show you a lot of lab data where we can recreate pressure, temperature, and the amount of water in a magma or in the atmosphere and recreate those conditions to see what happens. And so what we did here was there you go, sorry. We took magmas at high pressure, high temperature, and crystallized them to see, okay, at what conditions do we form the results and the similar chemistry that we've seen on Venus. And so if we use the Earth as a model, we can geochemically put all volcanoes into sort of 4 different categories. And I'm going to ignore here things like Mount St. Helens and Mount Fuji, where we have 2 plates colliding, because we have no evidence for that on Venus. So these are just volcanoes like Hawaii. Hawaii is actually number 1. Sorry, yes, Hawaii is number 1, and then some of the Hawaiian volcanoes are also number 4, depending on the exact volcano. If you've ever been to Iceland, Iceland is down here. It's this trend number 3. If you've ever been out west to Craters of the Moon and Snake River Plain, that's the volcanics from number 2. And those are just examples, but we can sort of dump everything into these 4 different categories and these 4 different things. And then we can use those analysis from Venus to see, okay, can we tell anything about what types of magmas? Do they look like Hawaii? Do they look like Iceland? And what does that tell us about how they formed? So here is 2 elements. So this is bulk rock potassium and bulk rock silica. The colors are the same as from back here. So I apologize. The colors are not the same because I pulled them from different papers. Sorry about that. So, but here's where we actually have the different volcanoes. So this is Thingmuli, which is on Iceland, the Galapagos. As I said, this trend in the middle here is Snake River Plain. Here is Hawaii. Here is also Ascension Island and Nandawar, which is a volcano in Australia that I did my part of my PhD work on. And then the yellow ones, which are actually really interesting, are a volcano called Tristan da Cunha. And if you look, these are the 3 analysis where we actually have bulk rock chemistry, Venera 13, Venera 14, and Vega 2. I'm going to go back for 1 second. Sorry, went too far. There we go. So this is actually the image from Venera 13. It actually had an arm that went out and took a piece of the rock, put it back into the spacecraft body and ingested it. So this is actually images of the rocks that, or the rock that it was analyzing. Okay, so Venera 14 and Vega 2, they plot down here. You can see the large error bar, but they sort of look like a basalt from any of these, with the exception of Tristan da Cunha. And based on this discrimination, we couldn't really say much more than it looks like a typical terrestrial basalt. On the other hand, just based on these 2, we can say Tristan da Cunha looks like lavas that would form at Tristan da Cunha, which is weird and unique and not sort of what you'd expect, which is pretty cool. And what we can do is, using what we know of the Earth, we can see where the magma chamber would have been and where this magma would have formed for all of these. And now I did color code the from here to the next one. So these 2 basalts sort of look like any. So the green, the blue, the light blue, or the gray, whereas this one looks like the yellow. And so for the 2, we can't really say much. All we can say is that they look like a basalt. The magma chamber could have been anywhere in this direction. We can't constrain the water content, but it looks like a basalt from the Earth. On the other hand, that one weird one looks like Tristan da Cunha. Well, Tristan da Cunha forms under very specific pressures. It's much higher pressure, 18 to 27 kilobars, which coordinates to a depth of 65 to 100 kilometers in the interior of Venus. It also needs a little bit of water, so 0.28% water in the magma itself. And I have a star here because it also, on the Earth, likely requires the presence of dissolved CO2. So we're looking at a magma in a magma chamber that has some amount of water and some amount of CO2. I saw someone in the chat. Is that a question? Sorry, I don't have the chat open.
I don't think we have any at this time,
Okay,
Doctor.
cool. Oh, okay. Yeah, so that's where we are with what we know about those three rocks. Well, we can also model sort of where they form and compare those again. There we go. We can compare those again with what we know of the Earth. And here is pressure temperature for two different sort of cross sections. This is for mid-ocean ridge basalt, so where two plates are pulling apart and magma is forming. And this is for Hawaii, and so we can compare them to see, okay, does the modeled pressure and temperature of these formation conditions match either of these? And you can see here, this is for Venus, and I've dumped all the data together for the moment. It's hotter than mid-ocean ridge basalts, but it looks very much like Hawaii, looks very much like Tristan da Cunha's would be down here, so slightly hotter than Hawaii. And so this matches a sort of ocean island hotspot volcanism for Venus. I'm going to skip that one. And so if we just sort of summarize, do they look like mid-ocean ridges? Do they look like ocean islands? Vega 2 and Venera 14 are consistent with terrestrial basalts. Because of the uncertainties, they are consistent with both a mid-ocean ridge or an ocean island. However, they're more like a Hawaiian style volcanism. On the other hand, Venera 13 gives us a very clear idea of what types of lavas these were. And this is consistent with rocks from Tristan da Cunha. They're called silica undersaturated. They have a deep origin, a little bit of water, and importantly, CO2 in the source region. And so this was really cool. It was the first time we could say something unique about the constraints of how these formed, as well as how much water was in the interior, and the fact that we also need CO2 in the source region for this. All right, so that's all of the chemistry I will throw at you. I just wanted to point out that Venus is very Earth-like. However, we're not going to have Mount St. Helens type volcanism. We're either going to have things that look like Hawaii, Tristan da Cunha, Iceland, or we're going to have things where two plates are pulling apart and forming a mid-ocean ridge type thing. So that image that I showed you on the first thing of this giant volcano with plumes of smoke and explosions, that's not going to be the volcanism. And so while space.com and ESA like to make things really explosive and really fun, it's going to look a lot more like Hawaii, which gives us our sort of stage for moving forward of constraining the age of these. So we can't use geochemistry to constrain the age. So our Venera and Vega data are interesting. They tell us where our baseline is, but they're not going to tell us about the age of the volcanism beyond what type it is. And so we need to move to other sources of data. Well, as I said, we have had orbiters. We've had radars, Magellan Pioneer, as well as Venera Vega. Because we can't, you can see here, this is Venus. You can't see with a normal camera down to the surface and take images like we can on the moon, we can on Mars. I mean, you can stand out in your backyard with a telescope or with a binoculars or a telescope and start doing geology of the moon, because you can see the features. You can see the bright areas and the grayer areas, and you know those are two different types of rocks. For Venus, we can't even do that from orbit. We need something that can get through that. And radar is how we map the surface. The other way is we can use spectroscopy. Again, for things like the moon, for things like Mars, we can map the entire surface with lots of spectral features and get really good mineralogy. And again, with Venus, our atmosphere and our clouds get in the way. And so we have a hard time there, but this is how we can age date the surface and age date some of these lava flows. So talking about how we don't have full data set, this is the topography of Venus, and you will see these white areas, strips down here. We do not even have full Venus topography. We do for the moon, we do for Mars, we do for Mercury now, but we don't for Venus. And just one thing to point out is here is Venera 9, 10, 13. You can see the volcano sitting close to probably where Venera 13 analyzed, and some of the other landers. The other thing you can see is up here, this is Highlands. So the brighter the color, the higher it is. The lower the color, the darker the color, the bluer it is, the lower it is. This does not represent water. It's just lowlands. But you can see we have something that looks like a giant continent on Venus, and we don't even know if that's granite, if it's just ancient crust, what this is. That's a whole other talk that I could give, but we'll focus on sort of volcanism. So this is where we are with Venus topography, and we can look at some of the volcanoes and look at their shapes and again compare them to the Earth. And so this is Sappus Mons. It's 400 meters across, it's 1.5 kilometers tall. It has a very gentle slope. You can see this is a radar image, so things that are brighter are fresher, things that are darker are older. As they age, they go in that direction. So iron is bright in radar, and so that's what you're seeing here. And here's a picture of Hawaii and some lava flows on Hawaii. Sappus Mons looks very much like Hawaii, smaller version, but in that regard. Okay, so another fun press release. This is one of my favorite volcanoes. If you look at this image, again, we've got these steep slopes, and it looks like Mount St. Helens or a Cascade volcano that should have giant eruptions. And you can see this nice, beautiful lava flow coming at you and toes down here. This is 20 times vertically exaggerated. And if you shrink it back down, that's what it looks like. And it looks like Hawaii. If you had an image of a cross-section of Hawaii, that's what it looked like. I also like this image because that's how I chose my background. It matches that. But if you were going by this, you would say, oh, look, it looks like that. Whereas it really looks more like that. And so this again is consistent with our volcanoes on Venus being Hawaiian style or shield volcanoes. The important thing for that and for me as a mineralogist is they have a green mineral called olivine in them. And so this sets up the next part of my talk of how do we figure out how old these are? So how old is the volcanism on Venus? And for that, I'm going to switch data sets, and I'm going to switch to Venus Express. So this is an e-submission. This is the Viridis instrument. Viridis is a spectrometer. The problem, and I'll show in a second, the problem is that most of the wavelengths for this get reflected in the clouds and we never see them again. So you can make great measurements of the clouds and what's going in the clouds with spectrometry, but only 3 windows make it down to the surface and back up. And they're all right around 1 micron. So you'd hope that they were all spread out because then you could see how the slope changes, but we can't. We can see how things look in 1 micron. And so this is work from Sappus Mons back in 2010, where they actually looked at how the light comes back or emission of these. And you can see here, the things we're looking for are the things that are red. So this is Imda Regio. And this is Idunn Mons. So this is a small volcano in Imda Regio. This has high emission, and I'm going to switch back and forth. So high emission is also low reflectance, because in the lab I can measure reflectance. From orbit we measure emission, but they're related. Emissivity is just 1 minus reflectivity. So if it has an emissivity of 0.9, its reflectance is 0.1. So, and I'll remind you that as we go and try to compare the two. So how can we use emissivity? And again, this is the issue. We've got cloud scattering, and we can get the 1.18 micron feature, which is the one I'm going to focus on because this is the one that gives us the most information about igneous rocks. So it provides information about mineralogy. Felsic minerals, so things like quartz that make up our crust, and alkali feldspars, that pink mineral, and if anyone has granite countertops, they have pink in them. That's a felsic mineral. Your granite countertops are felsic. These, as well as things that alter. So if we live in Houston and things like rust also has low emissivity. On the other hand, fresh lava, so if you took a rock from Hawaii, has high emissivity. Those bright red spots, I go back here, this high emissivity tells us that that's fresh lava. And so Jorn Halbert and Darby Dyer, just another graph to show you this. This is emissivity versus energy. And again, we're looking right here in the 1 to 1.1 micron band. Basalt is up here, so these are fresh lavas. As we go to things that make up kitchen counters, your granites are down here at 0.9. So we've got a drop in emissivity. But weathering also takes us in this direction. So weathered basalt, granite down here. They both take us in the same direction, and we couldn't be able to figure out the difference between a weathered basalt and a felsic rock from orbit just from this measurement. For what we're doing, that's okay. And so coming back to this is MCcarts' work, focusing in MDAR regio. We've got, this is topography up here, so height. This is emissivity here. You can see the emissivity of MDAR regio, and especially Idunn Mons, is about 0.9 or slightly higher than 0.9. So that is a very fresh basalt. And so what they published back in 2010 was that these were less than 2.5 million years old. They were possibly less than 250,000 years old. And this suggests that Venus is geologically active. To a person who studies a planet, planets are 4.6 billion years old. So 250,000 years ago, while seems old to a person, is actually really young geologically. However, they couldn't put an age constraint on this because they didn't know how quickly fresh lava alters in contact with this very hot, very caustic atmosphere, and how that affects this emissivity measurement. And so this is where I come in. As an experimentalist, this is what I did. I took fresh lava, so these are samples from my summer intern last summer. This is the original paper, so these are olivine crystals. Remember, I talked about the fact that basalt has olivine. If you go to Hawaii, once we're allowed to travel again, and you go to Green Sand Beach, these are olivine that are being pulled out of the fresh lava at Hawaii. And so I started there because this is a pretty ubiquitous mineral in lava. And then, as I said, we expanded this to a second paper that my summer intern worked on, looking at fresh lava, so basalt, and then other minerals that also make up lava called pyroxenes. And so this is different types of pyroxenes. I'm not going to focus, that's why I've graded them out here. This tells the most interesting story, the olivine and the basalt. The surface of Venus is 470. Our furnace doesn't like to quite go that low, and so we did it at 600, and then I've also done the olivines at 900. 900 isn't directly applicable to Venus, but it speeds up time. So it tells us what would happen in longer time scales, because we can't do experiments for years. We did do experiments up to 7 weeks. 7 weeks seems like a weird amount of time, but it was a 10-week intern program, and it took her a few weeks to get the samples prepped and analyze them. So it ended up being 7 weeks. And you can see we've got strings of 4 here. We pulled them out after 1 week, 2 weeks, 4 weeks, and 7 weeks. And so we've got a time progression both for the basalt and for the olivine. The olivine, I will give you a hint, reacted so fast that instead of waiting a week, we waited 12 minutes to pull out the first olivine. And then we went 12 minutes, 24 minutes, we went up from there to, and for these, we only went out to about a month. We measured them before and after because we want to see how they change. And so we wanted to look at the mineralogy, we wanted to look at the textures, and importantly, to compare back to MCcarts' results, we wanted to look at spectroscopy. So as I said, we can't do emission easily in the lab, so instead we do reflectance. But emission is just 1 minus reflectance, so there's that equation to remind you. And this is my spectrometer in the lab, and this is one of Kyra's basalt run products, and I'll show you. This is looking at the surface, and we can actually see the minerals changing on the surface. So first, starting with the 2020 paper, or my 2020 paper, since they both came out this year, and looking at how olivine changes. This is the 600 degree. This is the 900 degrees. These are in terms of hours. So 0, this is a month. As I said, olivine reacts so quickly that we pulled them out after minutes. This is for 600. You can see we've got beautiful green. These are gem quality olivines from San Carlos. There's some from China as well. So very typical olivine. You can see after a very short time, you can see this brown coating starting to form. This is like rust on the earth, except it's forming from olivine. You can see after 1 hour, 5 hours, you can see more of it, 25 hours, 125 hours, you can see it's starting to get very coated, and then 625, it's not fully coated, but mostly coated after a month. At 900 degrees, after 12 minutes, it looks the same as 600 degrees after a month, and so this tells you how much we sped up the reaction. But after a month, you can see it's not even shiny anymore. It's sort of this metallic, rusty color. And you can see we've got shards here. This was originally one nice olivine. The reaction actually increases the volume. It forms a different mineral called hematite. Hematite has a larger crystal structure than the olivine, and so it breaks the olivines apart and made a mess of my furnace while doing this. And so we learned quickly to put them in cups and try to keep things neater, but we made a mess. But anyway, so this is what happens to our olivine. So you can sort of see where I'm going with if we have fresh basalt on the surface of Venus, how much they've changed. But now let's look at the spectra. And again, I have this red bar here at 1 micron because that's all we can really see. For the basalt, for the olivine, I have them offset. So these are just stacked based on time. For the basalt, I'll show you how they actually change with time. And so you can see the dark green at the bottom. This is a beautiful, perfect olivine spectra. It's got a doublet here, an absorption feature, very flat, and then a feature out here. And so you would be able to see this very easily with an orbital spectrometer. And again, these have very low reflectance here. This is actually down at 0.08, and so emissivity would be 0.92. However, as we increase oxidation, and I'm using the 900 degree experiments because they showed more of a progression. The same thing applies to the 600, just again on a slower time scale. After a few hours, which is in here, this feature is gone. It's perfectly flat. So we wouldn't be able to see it from orbit for any of these. And then after a month, we actually have new features forming. This hump here, and there's a feature there and there and there. This is hematite. This spectra looks exactly like a pure hematite. Even though the sample still has olivine in its core, it has such a thick rind and a thick coating of olivine on the surface that that's all you would see from orbit. So we concluded that based on that 1 micron emissivity, if we can jump from olivine to a basalt and to a lava, that these lava flows can only be a few years old at most, which is a great conclusion. And we felt really comfortable publishing this, but we really wanted to figure out what basalt does, since lava is not just olivine, it's olivine plus other minerals. And so that's where my interns project came in. And so this is the basalt unaltered in the lab. This is a scanning electron microscope. So we're looking down a microscope at this. The different shades of gray are all different minerals. Here is a nice olivine crystal. This is basaltic glass. So when basalt cools really quickly, it turns to like obsidian, it turns to glass. And so we've got glass in here. We've got some pyroxenes, some bright colored crystals. Everything looks nicely. There's nice sharp edges everywhere. And this is because there's nice big vesicle bubbles. So this is where gas was escaping as this lava crystallized. This looks like a beautiful, relatively unaltered basalt. And after 2 months at 600 degrees, this is what it looks like. And you can see all of these little bright dots all over the surface. they're focusing on glassy areas and they're focusing on the olivine. So you can see an olivine here that's now bright. This is the mineral hematite. Hematite is oxidized iron. And so the iron is coming out of the olivine, it's coming out of the glass, it's oxidizing, and it's forming this new mineral. It's more or less rusting on the surface of my samples. And so if we look at spectra, these have not been offset. We did it first, and then we realized how much change there was in 7 weeks, and so we decided not to. This black line is the basalt. Well, basalt doesn't have much spectral features because it's a mix of lots of different minerals. But remember, olivine has that nice broad feature right here, and you can see this sample has olivine. There's a nice broad feature right here. Well, as we increase alteration from 1 week, 2 week, 4 week, 7 week, the first thing you can see is the reflectance gets much brighter. It goes from less than 5% to over 15%. And that's because those bright spots, all of these little bright spots reflect light a lot more than this nice big olivine crystal. And so these are all reflecting light. The other thing you can see is we have new shapes. So we've got a new feature here and a new one out here. And this looks just like the same thing that I showed you with the olivine, where we've got a spectral signal of hematite. And so again, we're seeing this shift from basalt and lavas to hematite coating the surface. And again, even though hematite is not coating the entire surface, you can still see evidence of other minerals. The hematite is so bright that that's what's dominating the reflectance. So remember, if you think about this in terms of emission, this would be an emission of about 0.95. This would be emission of 0.8 to 0.85. And so if we look, compare this to Idunn Mons, we've got emission here, especially right here on this lava flow, of 0.9. Well, that has to be fresh lava. And then you can see we go down from there to lower emission. Well, that tells us that this is probably the youngest lava flow, and these are probably older. And here we're seeing a lava flow that's probably, I mean, if we use this as our estimate, it can't be much older than a few years old, because we would start seeing a degradation of this 1 micron feature. And so again, this confirms what we saw for the olivine, that these lava flows at Idunn Mons cannot be older than a few years old. And we've done this with single crystals. We looked at olivine, which dominates a lot of lava flows. We did this with the basalt itself. We also did this with the other main mineral in lava flows, which is called pyroxene. If these lava flows are pyroxene rich, they're possibly, and this is where it's in parentheses, up to a decade. So that's where, since we don't know the exact chemistry and the exact mineralogy, if they're dominated by olivine, if they're dominated by glass, they can only be a few years old. And if it's truly olivine and glass, they have to be less than a year old. If they have some pyroxene, they're probably a few years old. If they're mostly pyroxene with some of the other minerals, they're likely a decade or so old. And so this tells us at least the lava flows at Idunn Mons are relatively, or are young. I showed you the picture of St Mons, which was the one that was really over-exaggerated. St Mons is a great volcano, and based on radar is probably also quite young. But we don't have spectroscopy. We don't have emission for the entire planet, and so we don't have data for St Mons. And so this image, which space.com used, ESA originally should really look like this. And this is the Hawaiian lava flow from 3 or 4 years ago now, where we're going to have a lava flow. It's going to stop. Another one may come in a decade or so and flow over it and then stop. And this is what the volcanoes really look like, or at least what we think they look like, where they're much more Hawaiian style of these runny lava flows coming out. And so instead of stopping on my intro slide, I'm going to stop on where we're going, because this comes up a lot, is are there new missions to Venus? We haven't had one in forever. And the first time I gave this talk, this slide was rather depressing because there was not much on here. And I can happily say that at least things are moving in the right direction. This year, NASA has selected 2 new missions for planning. So we're in phase A, planning. Neither may fly. We'll find out if one will in the spring, in spring 2021. But there's a mission called Da Vinci and a mission called Veritas. And Veritas is run by Sue Smakar. You'll notice that name. She was the person who led the original paper about Idunn Mons. That's a orbiter looking at radar and an imaging spectrometer. So we can finally get both topography and spectroscopy at the same time for the entire planet. The other mission, which I'm a co-I on, is called Da Vinci Plus, and this is it's a 2-part mission. One is an orbiting spectrometer focused on the northern hemisphere, and so we'll get Map Mons, we'll get that continent to see what it is. The other thing, we're an atmospheric entry probe, and so we're going to dive into the atmosphere and see what the chemistry of the atmosphere is, and take a look at the surface underneath the clouds. And so we'll be able to get better resolution of what's going on in the geology. Unfortunately, because we're an atmospheric probe, it also means we're going to burn up, and so we are a few-hour mission. But we also have the orbital component, and so we'll have really cool results to combine the 2. The Russians are at least talking about restarting their Venera program with the Venera D mission. It would have a launch date in 2026, although I've heard rumors that that's slipping already because they're still in the planning phases. NASA is at least talking about working with them, potentially providing instruments. And this would be, again, just like the old Venera missions, an orbiter and a lander, not just an atmospheric entry probe. And then ESA is getting involved as well with an Envision mission. This is a longer term project where, if it is selected, would launch in 2032. NASA is on board again with this. This is a high resolution radar mission to map the entire surface. And so that is my last slide, and I'm happy to take questions and talk about why Venus looks like this and not this.
Excellent. Thank you so much for the talk, Dr. Filiberto. That's absolutely fascinating. We did have a few questions pop up in the chat. So Bill Spitzeri, I think, was the first one to ask. Bill, do you want to unmute yourself and ask your question?
Sure. I was fascinated by your Hematite Olivine connection there. I do meteorites a lot, and I see Olivine all the time. Does Hematite always originate as Olivine, or does Hematite exist other ways?
No, Hematite forms by the oxidation of iron. So
Okay.
It can come out of olivine, it can come out of glass, it can come out of other minerals as well, as long as there's iron around and you have either water. So I study Mars a lot, and we have a lot of hematite on Mars, and a lot of that's from water rusting the surface, making hematite and things like that. For Venus, there's no water, but with the atmosphere that we have and the temperatures we have, the hematite forms from oxidation.
Okay, so it's because of the heat on Venus that made the transition.
Yep.
Okay, I have one more question, if I may. Your photograph of Venera 14, I remember seeing, I'm old, so I remember seeing it when it went up. The top of it looks like a big screw. I've never seen that on a spacecraft. Do you have any idea what that's all about? The big silver cylinder has a screw-like pattern on it.
Yeah, I don't know that much about the engineering of Venera and Vega missions.
Okay, thank you.
It's kind of like a big light bulb, right, Bill?
Yeah, I don't know what that is. Some obscure mechanism.
All right.
I suspect it's actually antenna. Looks like a kind of an antenna that might be used on this thing.
Right. Point. Okay. Joe Dellinger, I think you had a question as well. Did you want to unmute yourself and ask?
Sure. Yeah, I was going to ask, are there any plans to do, I mean, if you think that there's changes happening on the surface, you should do synthetic aperture radar interferometry, because then you would be able to see changes. I mean, if it really is still volcanically active, that would probably show up pretty easily.
Bruce Campbell works with Arecibo Observatory, and they've done radar measurements regularly, and they haven't seen changes. However, the problem is radar has a thicker penetration depth than VISNI IR, and so if these lava flows are thin, radar may not see it. But yes, it is one of the, it's something that the Arecibo people and other radars have been looking for. And my hope is that if we take one of, if I'm hoping Da Vinci gets selected, but if not, if Veritas or Envision fly and we get a orbital radar where we can measure the same spot multiple times and look back, that might also be able to help us see this. The other thing is with ground-based radar, your spot size is larger, so we need something in orbit.
Yeah, I was thinking like an orbiter. Are they going to put a SARI on an orbiter? That's really what I was trying to ask.
Yeah, so I don't know what radars on Veritas or Envision, but they both have orbital radar instruments.
SARI is near and dear to my heart because Professor Fabio Rocca, who invented it, was actually at my research group at Stanford in geophysics when he invented it, and he got censored for about 5 or 6 years. Basically, the military people stopped his publications and said, "We'll give you money. Talk about this to no one." So people usually think it was invented like in the 90s, but it was actually invented in the mid 80s. It was just hushed up. So it was an interesting experience.
Yeah.
All right. Thank you very much, Joe. Great question. Don Selly, I think you had a question as well, correct?
Yes, Dr. Filiberto, I'm assuming because these are shield volcanoes, they're similar to Hawaii. That means the magmas are fairly not. I'm not sure what the word is contrary to viscous. They're non-viscous. They flow very well. Correct?
That's correct. Yeah, and you can see here while this image is vertically exaggerated, it does show these lava flows nicely, and you can see the sort of toes down here that look just like the lobate structure that we would see at Hawaii. So yeah, they should have viscosity similar to Hawaii.
So again, does that what drives that? Is that from the water content or?
Viscosity is a combination of temperature of eruption, chemistry of the lava, the amount of bubbles in a lava, the amount of crystals in a lava, and the water content.
Okay, so the short answer is it's very complicated.
The biggest two are temperature and chemistry. So. And those two are linked. So a runny lava like this is going to be higher temperature, and it's going to have a chemistry similar to Hawaii.
Okay,
and so that's how we know these are basaltic lava flows. Rhyolitic lava flows have a very different structure to them. So they're much stickier. They build high piles. They don't go as far. You don't get that nice lobate structure at the end.
Thank you.
Dr. Filiberto, do you have time for another question or two?
Yeah, we're good.
Okay. I think Debbie Moran had a question that she had asked in the chat. Debbie, did you want to ask that?
Yeah, I mean, this is just a shot in the dark. Are there any local atmospheric effects from these volcanoes, especially since Venus has such a slow rotation rate? Or is anyone even looking at that? That may be impossible to study.
That is an awesome question. And yes, people are. And yes, we've seen sulfur plumes in the atmosphere from these orbiter missions. And the idea is that these sulfur plumes, one of the models is that they're releases of volcanism, releasing their sulfur to the atmosphere. But again, because they didn't have a pinpoint of the lava, it was sort of a working model. And this suggests that maybe the lava flows at Idunn Mons were the ones that they were measuring from orbit.
Cool.
All right, great question, Debbie. Thank you. Anybody else have any questions they may want to ask?
There was one from Frank Private.
Okay.
Ultrasound instruments. I don't know of any ultrasound instruments. Again, I don't know all of the instruments on the other missions exactly. We do not have one. Then I thought I saw another one. Oh yes, James asked, what is a few years old? Is that space-time or human time? Usually as a geologist, I'm talking geologic time or space-time. Here I'm actually talking human time, that these lava flows are probably a few years or a decade, possibly 100 years old at most, depending on the exact mineralogy. But we're talking lava flows human time, not space-time.
Excellent. Thank you. All right. One last question, if anybody has one. Go ahead and unmute yourself and ask. All right. I think that's it. Dr. Filiberto, thank you very much for your talk. I think this was
Thank you.
a fascinating discussion. And I think as much as we send craft and orbiters and whatnot to Mars, you know, this has kind of piqued my interest, and I think you're getting more and more people jumping on the side of more exploration of Venus. So
yes, and as I said when we were talking offline, look for a press release about some really cool new results on Monday for Venus that may change what we think about our sister planet.
excellent.
So I'm not a co-author on the paper, but I know it's coming, so
Certainly.
keep an eye out for that. So
we'll look for that, and we'll disseminate that across the entire club here. So thank you very much for that, and wish you all the best in your continued research on Venus, and hope that we're able to get something up there soon so that we can kind of further advance the work that you're doing. Thank you very much, and thank you everybody else for joining us tonight. Really enjoyed the time here. Remember, our next meeting is Friday, October the 7th, 2nd, I should say, at 7 p.m. And if there's anything else you need, please feel free to reach out to us. But until then, we'll see you then. Thank you very much.
Don't forget about novice the day before.
Yes, we will have a novice meeting October 1st, Thursday, October 1st.
Thank you.
Our novice meeting, and Bill Spitzieri will be giving that particular talk. And then our meeting with Walt Cooney on Friday, October 2nd. All right. Thank you all. Have a good night.